Hello, in this video I'm going to talk about electromagnetic waves, a topic that comes up in pre-university physics but can create a lot of misconceptions. Because if you recall, right back at the start of this series of videos, 200 videos ago or whatever it is, I was talking about physics being how we're describing phenomena in the world around us, how the universe behaves at its most fundamental level. And those descriptions we could broadly categorize in terms of classical physics, as in the physics that was done prior to the 20th century, give or take, and then modern physics, which was ushered in by Einstein and colleagues in the early 20th century when they started working on things like relativity and quantum mechanics. Now, electromagnetic waves, a lot of the difficulty that we have in understanding electromagnetic waves before we go off to university is the fact that we are well and truly sat inside classical physics with what we're learning. And a lot of the answers to fairly obvious questions, the difficult answers to those obvious questions, sit inside modern physics, and we're not ready for that yet. So this is where a lot of misunderstandings and misconceptions can creep in. So what I'm going to try and do in this video, and it'll probably have to end up being over 2 videos, there's going to be quite a lot to say, is to run through the sort of content we need to know about in pre-university physics on electromagnetic waves and just try to tackle some of those misconceptions that seem to come up quite a lot in the tutorials that I do. So what can we say, first of all, about an electromagnetic wave? Well, we've been talking about waves over a number of videos now, saying that we've got some disturbance of something. We'll get back to that. And that disturbance then propagates through space. So here, in the case of an electromagnetic wave, we've got a disturbance that's related to the electromagnetic interaction, as we spoke about in the structure of matter section. So that's the sort of disturbance that we're dealing with here. As to what it is that's being disturbed, we will come back to that in a minute, because we've got an obvious question here. We know that light is an electromagnetic wave. We know that light travels through space. We know that space is a vacuum or near vacuum. So it does raise the obvious question of, well, what is it that's oscillating? We've been talking about water waves and waves on strings and things like that. Well, we can see what's oscillating there. Here we've got a bit more of a problem. So hold that in mind for the moment, and we'll come to that in a little bit. But in terms of the actual electromagnetic waves, there's a lot of different names for different types of electromagnetic waves. Now, they're all the same phenomenon. They're all electromagnetic waves, but as they were being discovered, people didn't necessarily know that they were all the same phenomenon, because electromagnetic waves can behave very differently depending upon the frequency or wavelength or energy, it's all interrelated, of the wave. So, an X-ray, which is an electromagnetic wave, behaves very differently to visible light or microwaves. We know, X-rays pass through a lot of things a lot more easily than visible light. So we're seeing very different behavior, even though it's the same type of wave. So this is where one of the first things we need to learn about electromagnetic waves is the electromagnetic spectrum. So if we're going from one end being high energy, high frequency, or we could say short wavelength, and we're going to the other end of being low energy, low frequency, long wavelength, then we need to be able to draw in and name, and say some of the property, quantify these wavelengths. Is the main thing. We need to say something about these and the names of the different parts of the electromagnetic spectrum. Right, so the way that I tend to build this up is I start with red. The visible light we draw in the middle is a very narrow band of wavelengths that make up visible light, but we'll draw this in the middle. I'm going to start with red. So if this is where red light is, red visible light, and I always start here because I find there's 7 colours in the rainbow, 7 times 10 to the minus 7 meters. That's the wavelength. And I've always used that. It's just stuck in my mind as a way of fixing something. So we're going to higher energy, then we're going to get violet, the other end of our visible spectrum. Is going to be off to the left. It's at shorter wavelength, it's at higher frequency, it's at higher energy. So I'm going to take off 3, the number of letters in red, to give 4 times 10 to the minus 7. That's our wavelength of violet. So we've now got those bedded in place here with our visible light in the middle. And it's quite easy to fill in a lot of the names, at least. If we're going to a longer wavelength than red, then we've got infrared. If we're going to a shorter wavelength than violet, we've got ultraviolet. If we keep going towards the longer wavelengths, we then get microwave and radio wave. And if we keep going to the shorter wavelengths, we're going to get X-ray and gamma ray. So in order to quantify these a little bit more, I mean, they don't have rigid boundaries between each one of these different sections. So providing you're getting something in the ballpark. What I tend to go for is thinking of X-rays being about an angstrom. So they're around 10 to the minus 10. Okay, you're going to get, 10 to the minus 11, 10 to the minus 9, you're still in the ballpark. But it's then saying something about, what these other wavelengths are going to be. We must have around about 10 to the minus 8 for UV. We're going to, if you go to 10 to the minus 15, we're well into X-ray. And then if you give something that's in the, in the gaps between those, then that's going to be fine when they ask you in an exam question. If we're going to the other end, then the dividers I normally use on either end of microwaves is we've got millimeters and centimeters. So if you've got something which is in the order of a few millimeters up to a centimeter or thereabouts, then you're well and truly in microwaves. If you start getting up into meters, you're well into radio waves. And then you've got infrared just sitting here between the millimeters and the red bit. So as I say, it's all a little bit fuzzy, the boundaries, but ballpark stuff is fine. And I mean, another thing which is very different with the behavior, which will then come up, seeing as we're in the optics section, is going to be coming up soon. Transmission through the Earth's atmosphere. If we want a ground-based telescope, then really we're observing visible, maybe short end of IR, and then a bit of radio. So if you want to be looking at anything else, if you want to be looking at microwaves, middle of the infrared, UV and X-rays, anything like that coming from space, you need a space telescope. You're not going to be observing those on the Earth, which is quite good. We don't want to be getting completely fried by UV, X-rays and things like that from outer space. So having a bit of protection there certainly goes a long way. So that's set up those. Now let's get back to this question of what is it that's oscillating? How is an electromagnetic wave actually propagating through space? And this can get quite confusing because really the answer to this, as I said earlier, is sitting inside quantum mechanics. We're not there yet. We want to talk about something in classical physics, and we can see why this is a problem. I mean, the physicists back in the 18th and 19th century spent ages trying to work this out as to what was going on. They were searching around for some medium, what they were calling a luminiferous ether. They were searching for this as it was thinking, well, this must be what permeates the whole universe. It's some substance or something which is oscillating, which is allowing these waves to propagate through space. Now, of course, it turns out that this thing doesn't actually exist, as shown by the Michelson-Morley experiments. I see my video on that, which will be coming up soon. Something is oscillating, but there is no thing. There is no matter there. Right, so how are we going to at least get a primitive description of this? So think of, say we had a static electric field. So we've got a charged particle, because everything to do with the electromagnetic interaction is to do with electrically charged particles. And as we know from our structure of matter section, the gauge boson, which mediates the electromagnetic interaction, is the photon. So we've got charged particles, things like electrons, protons. Of course, protons are getting their charge from the quarks that are comprising them, and they are interacting in certain ways, and anything which is involved in that interaction is mediated by the photons. So we've got this electric charge, it's sitting here in space, it's got an electric field around it, it's just a static charge not moving, so we've got an electric field, which is a static electric field. But then what happens if the charge moves? So if the charge moves, we've then got a disturbance related to the electromagnetic interaction. That's going to cause an electromagnetic wave, because if the charge moves over here, well, the electric field has changed. That change, that disturbance, needs to propagate through space. I mean, it does propagate through space at the speed of light. And the thing that we also get with this is when the charge moves and we've got this disturbance, we've got this changing electric field, well, that also gives us a changing magnetic field. So we've got two fields that are oscillating. And when you see waves drawn out of electromagnetic waves, you quite often get these two fields. You'll get one of them which is going in and out of the screen. So imagine that being sort of flat, with drawn out horizontally, where this is going in and out of the screen. So that might be, I don't know, well, that could be either component. And then you've got another one which is going up and down in the plane of the screen. So we've got these two waves which are interrelated with each other. They're both sinusoidal. So we've got one of them that could be our electric field. I'm just going to try drawing it again because it's just so hard to draw them on here. And then perpendicular to it, we've got this magnetic field as well. So we've got the two components here of this electromagnetic wave propagating through space. This is all described by Maxwell's equations, which we'll get onto in more detail when we get onto the section on electromagnetism. But yeah, Maxwell's equations are our classical physics description of how these oscillations behave and interact and propagate and such like. But yeah, the real description for the full detail of electromagnetic waves sits inside quantum mechanics. And a big part of that is because although we're talking about these as being electromagnetic waves, and as we'll see shortly in a couple of videos time, the Young's double slit, Thomas Young, he did his experiment, Young's double slit experiment that he did, I think it was in 1801, and that demonstrated the wave nature of light. But quantum mechanics, at its heart, we've got wave particle duality. So we can treat these disturbances as waves, but we can also treat them as particles. So we can talk about photons as being a particle, and we can talk about them as being a wave. And this isn't just the case of saying, oh, well, here are two classical physics concepts. We can think about waves and we can think about particles by going back to our classical mechanics and thinking of it like a tennis ball being thrown around or whatever. We're not just doing that and then saying, oh, yeah, well, photons behave like both of these things. When you actually get into the quantum mechanics, which, as I say, is beyond what we're doing at the moment, then there's a whole new way of actually describing this. But all we can really do when we take our first steps is to try and build up some primitive image of what's going on. So we've got this initial image of electromagnetic waves, thinking of the oscillations of electric and magnetic fields, which pretty much culminates in Maxwell's equations, if and when we get to it. And then we've got this idea of photons as particles. Now, this is something where we really, really don't want to get the wrong idea about what's happening with photons, because I hear this quite a lot, that when people start to switch over thinking, okay, well, actually, these are particles whipping through space, these photons, that they start thinking that the photons are wiggling around as they're coming towards us. Now, the photons, as particles, are moving in dead straight lines, or at least dead straight lines while we stay in the world of Euclidean geometry. the idea of a dead straight line kind of changes a bit when you get into relativity. But parking that for the moment and just talking about particles, photons as particles, they're moving in straight lines. They're not wiggling around. There's no variation in their path or the flux of the light, the intensity. There's not some change in intensity. These are just photons which are whipping along in straight lines from source to observer. So that is what's happening with those. So don't start building up incorrect images in your mind that are going to be awkward for to unpick later on. There's not a lot that we say about photons in pre-university physics, but they will come up again in the sort of early bits of quantum mechanics that we're going to do later on. So at least don't get mixed up between the wave profile of the electric and magnetic fields, all of our sine waves, and the motion of the photons. A photon isn't some particle in the medium which is oscillating transverse. That is not what's going on. It's moving. Photons are moving in the direction of wave propagation in straight lines. So don't get them mixed up with being, it's the matter that's oscillating or anything like that. The photons aren't oscillating. So as I say, just keep that clear in your mind. Right, this might be a good point to stop this video because it's already getting a little bit long, and then I can come back in the next one to talk about refractive index, coherence, polarization, things like that, just the other main topics that we have to get through.